So, you would recall that in our previous lecture we had discussed what are immobilized enzymes, why should we immobilize enzymes, and what are the requirements of immobilization of enzyme, and the three major requirements, that is a soluble enzyme and the carrier and method of immobilization. We were looking into their characteristics. The soluble enzyme, as we all know, required for immobilization must have certain properties, that is, it should possess high specific activity and also desirable functional properties that are required for use of the immobilized enzyme. Besides that, the carrier must also have certain properties like porosity, that means large surface area, so that a heavy enzyme loading can be given to the immobilized preparation. And we were talking of methods of immobilization. Now, a large number of methods of immobilization are reported in literature. Most of them can be classified simply into three major categories. One is carrier binding methods, most methods where we take either a prefabricated carrier or a carrier for conditioning, either activation or some conditioning, and couple that to the enzyme with a physico-chemical interaction. It could be a covalent bond, it could be some non-covalent interactions, and those methods fall under carrier binding methods. Typical examples are adsorption, covalent binding, with which we will be discussing them in detail. The other method is cross linking. As you know that the enzymes themselves possess a large number of functional groups which can be made to react to each other and thereby aggregating the molecules and making insoluble in water. The aggregates will be insoluble and they can be used for as a immobilized preparation which can be readily separated from the liquid phase. Just to repeat, the cross linking refers to linking more than one enzyme molecule through their functional residues present on their surface. Most of the enzyme molecule will have a large number of functional residues. They may be hydrophobic groups, they may be electrostatic charges or other functional residues, and they can be linked under certain conditions, of course under ambient conditions, so that the inactivation is not allowed, and under those conditions aggregates of enzymes can be made which can function as immobilized enzyme. The third type of methods are entrapment methods, where the enzyme is entrapped within a matrix. It could be a gel, it could be a microcapsule, and thereby you could provide them an environment which is contained, which is very analogous to a living cell, and then use them as immobilized preparation. So, you can see that a large number of methods are available. Under each category also there are a number of methods, and we need to choose a suitable method for a particular purpose. And of course, there are no general rules. It often goes by trial and error, and of course, some available information. Now, for example, if you have to look for out of the methods available, which we will discuss subsequently, if you have to choose the immobilization method, let us say which one to use for a specific application, there are four distinct parameters which should be looked into, and I think the first and probably the foremost is yield of immobilization. That means, during immobilization procedure, what is the loss of enzyme activity, because there is no method which can give you 100% recovery of the enzyme activity that you have put into the system, and there will be some enzyme which will be deactivated, lost during the immobilization, and obviously the loss of enzyme activity has to be kept minimum for all practical purposes. And when you consider, the yield of immobilization is basically a term which can be considered on the basis of material balance. That means, if you take let us say soluble enzyme, add to a carrier, I am just giving a general sort of a kind of a and allow it by any method of immobilization, what essentially we are going to yield two streams again. One will be your residual enzyme activity in the supernatant, which is left uncoupled, and an immobilized enzyme preparation. Yeah, this is the total sort of picture of all the species that will be available, and essentially the loss of enzyme activity, if I call that your soluble enzyme activity is, let us say, E naught, your residual enzyme activity is, let us say, E r, and the immobilized enzyme activity is E I, then essentially your loss of enzyme activity is E 0 minus E r minus E I upon E naught, that is your loss, or rather fractional loss of the enzyme activity. You see, of the total enzyme activity, there is the activity is distributed into two fractions, the immobilized enzyme as well as the uncoupled enzyme in the residue, and still these two theoretically should combine and form the total value of E naught. But very often you will notice at the end of a method that there is some still balance left, and the balance is the loss due to deactivation during immobilization, and therefore, similarly the yield of immobilization again we also define as E I upon E naught minus E r. Now, I think very often there is a confusion in reporting these terms, and that is why I have tried to put them on in the form of an expression, that while we talk of yield, we must keep into mind the residual activity in the supernatant. It is not on the total enzyme, because part of the enzyme has been recovered in the supernatant, which if desired can be recycled, and therefore, the yield will be the activity which is recovered in the immobilized form divided by E I E 0 minus E r in the residue. So
all the enzyme that is immobilized is active. Whatever enzyme is bound to the carrier is active.
You see, when you talk of E I, that is the activity of immobilized enzyme, you are measuring in terms of the activity only.
Yes, sir.
So that means it is active. You see, as I think right in the beginning probably I made it very clear that when we talk of enzyme, quantification of enzyme is not done, it is just not a physical quantity like mass or concentration. It is a functional activity, it is a functional property, its quantity is a functional property, and activity represents functionally active. We are not measuring E I in terms of protein content. I am saying all these terms I am measuring E 0, E r and E I in terms of catalytic activity. So it is functional. And as a matter of fact, this loss, and that is why if it is a let us say physical quantities like protein concentration, the balance will be perfect. You cannot account for any loss of protein in the system. It is only the loss of activity because of the conformational changes. The other factor which is important to be considered is enzyme loading. That means that becomes the almost a similar parameter like what you consider in the case of a soluble enzyme, specific activity. You see, when we talk about specific activity, higher the specific activity, the enzyme is catalytically better. Similarly, in the case of enzyme loading, we talk of, for example, international units per gram of carrier, or if you take into account the bulk density of carrier, you can also say international units per ml of carrier bed. That means you pack the carrier into a packed bed, and then consider the volume. So you can express them in either quantity, either as international units per gram of carrier loading, or sometimes we can also refer them in terms of volume, because this is the volume, and so thereby it can be compared directly to a soluble enzyme. And so enzyme loading is another factor, and we want a preparation usually as high loading as possible theoretically. Of course, the enzyme loading will also have a very direct linkage with the mass transfer limitations also, which we will see subsequently how mass transfer and the catalytic activity are linked. Then the third parameter which is important to look at is storage and operational stability. Now, as I mentioned that we have to look for the enzyme, and one of the major advantage of immobilized enzyme is that they can be reused, they can be repeatedly used, continuously used, and therefore the stability, I mean, they must possess a much higher stability than the soluble enzyme. and this stability is not only in terms of use, but also during storage, and this parameter is usually expressed in terms of half life, either half life during storage, that means in what time the activity loses to 50% of the original activity, or during use in a continuous reactors or in a batch reactor, then in terms of number of cycles. Yes.
So we load enzyme on a sheet or surface somewhere. So why the unit is in IU per ml or IU per gram? It should be around meter square or meter type of thing.
You can express in that term also, but that will be only restricted when you are talking of a fiber or a surface. Very often, and the most commonly used matrices are beads, spherical particles, and that is why gram or volume, and they are packed in a packed bed. When I say per ml, I am referring to a parameter which is analogous to use in a packed bed. But of course, if your use is in terms of let us say a surface, in terms of fiber or on a film, you can also express in terms of surface area. I mean that is always allowable, but for all industrial application, the surface, excepting for biosensors and things like that, which are very specific applications, for catalytic for industrial catalysis, it is used in the form of particles and used in a packed bed. Well, we will discuss those aspects subsequently, but of course IU per meter square also is a feasible loading parameter that one can define. Then the fourth property, which is very important on the basis of for choosing the immobilization method, is the carrier cost and regenerability. Because each method has a limitation of the choice of carrier. For example, in the case of adsorption, you require a carrier. If suppose you want to adsorb by ionic binding, you need a carrier which possesses charges. Similarly, if you want a covalent binding, you need a carrier which possesses certain functional residues which can be coupled to the enzyme, and so on. So each method will have some limitations on the choice of carrier, and therefore the cost of the carrier, and even in spite of the cost of the carrier, I think another parameter which must be taken into account is regenerability. Very often even after the immobilized enzyme preparation has been exhausted during use, the carrier can be recovered and reused. So basically the cost of the carrier must be taken into account in terms of per cycle, not the absolute cost. You must differentiate between the cost, absolute cost, and cost of the carrier per cycle. And because many of the carriers, although expensive, but they can be used for a long period and in number of repeated cycles, and therefore they are still acceptable and desirable because of other desirable properties. Now the first probably and the simplest method of immobilization is by adsorption. Of course the adsorption method is a very broad non-specific method, and it involves binding of the enzyme to the surface of an insoluble carrier that has not been specifically functionalized for covalent coupling. Now I must make here particularly the phrase specifically functionalized for covalent coupling. Now I must say that this probably gives you an idea that this is a very broad non-specific method. Only thing which we are excluding from carrier binding methods, if considering all the carrier binding methods, excluding those which involve covalent linkage, rest of all the methods, rest of all the bindings, interactions between the carrier and the enzymes are covered under the term called adsorption. So basically a very broad based method which involves a number of non-specific multivariant reversible interactions between enzyme and the carrier at mild conditions. Now this second point also builds in a number of phrases. For example, the interactions that are involved are non-specific. Very often more than one interaction is taken, is involved in a particular method. Multivariant, that means more than one physical property is employed. In most cases the methods based on adsorption are reversible in nature. That means under certain conditions while you can adsorb the enzyme onto a carrier, you can also create conditions by which you can desorb the enzyme. And the basic property of its reversible interaction also makes it a weak binding. Weak binding in the sense, while during use the enzyme can also desorb slowly, of course, over a long period of time, and the if the carrier characteristics are sturdy, they can be regenerated and reused. But enzyme loss can be there with time, over a long period of time.
So just repeat what is multivariant?
Multivariant means that more than one physicochemical interaction is involved in binding. Then I think another property, another feature is mild conditions. Of course, that will apply to most of the immobilization methods and also to adsorption. That means the adsorption conditions, the environmental conditions required for adsorption must be mild, and here I think I like to very specifically define the term mild. Mild refers here not to the value 1 or 2, it refers to those conditions under which the enzyme is conformationally stable. The definition of mild condition refers essentially to those conditions which are environmentally acceptable to the enzyme. Now, one can go, if the enzyme is stable at 70 degrees centigrade, I think 70 degrees is acceptable and can be considered mild. But if enzyme is not stable even at 20 degrees, you may have to go to 4 degrees to immobilize, and the definition of mild will remain at 4 degrees. I have not used purposely the word ambient, because then you refer it to a very definite range. Then of course, an advantageous situation is that usually the methods based on adsorption result in high yields on the basis of, I mean, we have given the definition of yield, that means the total amount of activity which is resulting in the immobilized preparation is reasonably high, almost in the range of say about 70 to 90%. Enzyme activity is recovered in the immobilized preparation, and because the conditions are mild, they do not tend to cause conformational change. So, that is a very plus point as compared to other methods in which the yields may be much lower. A disadvantage is that the preparations do not have very high operational stability. As I mentioned, that the method is reversible in nature, the interactions are reversible, so operational stability is usually not very high, although by various other manipulations like adsorption coupling with cross linking, the operational stability can be improved, but intrinsically adsorption based methods are usually operationally, again when I say the term high, it refers in the comparative form, and the comparison here is with covalent binding. If suppose in the case of covalent binding, our half lives of the order of few months, here it may be of the order of few days. So, that is what it refers to, and then but allows regeneration of the carrier. But on the other hand, although the operational stability is not very high, but the advantage is that the carrier can be regenerated and reused, that is a plus point. Then of course, you have a large variety of carriers that can be used. We will look at some of the examples of the carriers, and finally, adsorption based methods have been very often used to study the enzymology of systems that naturally occur in biological systems, because in case of living cells, most of the enzymes are supported on a solid matrix through adsorption only. There are no covalent linkages. Either they are supported on membranes or they are supported on certain particulate matters, all the enzymes, and therefore, the methods based on adsorption are usually very analogous, similar to those that found in the living systems.
So, how do we define the operational stability?
Operational stability is we define in terms of half life. That means, for example, as I mentioned earlier, if you consider let us say the use of immobilized enzyme in a reactor, take for example, you pack it into packed bed, feed in and effluent out. Now, you just consider this operation here, if it is operational time, mind you, this is the operational time and this is fractional conversion, then what you notice is that you start at 0 time, the fractional conversion will keep on going down. As the enzyme activity is reduced, is lost, the fractional conversion keeping the residence time constant, and over operational time, this is operational time, not the residence time. Residence time is constant here, it will go down, and if you consider as a first order process, then the half life of this, that means the time it takes to reach the 50% of the original value is the half life. For example, in the case of a if we consider E is equal to E naught E0 E0 minus kd into t, you can simply calculate your half life as 0.69 over kd.
So T half is more in the case of adsorption.
No, T half is less in the case of adsorption, other way, compared to covalent binding, right, because it is, the interaction is reversible in nature, so it keeps leaking. In fact, a very crude term could be that the enzyme keeps leaking while used, very small of course, slowly, not in a very fast rate. As a matter of fact, this property of leaking of the enzyme from immobilized preparation has been very advantageously used in many cases of the enzymatic therapy, enzyme therapy purposes, where we want to put a immobilized enzyme preparation on site at a site where the enzyme is required, and the enzyme must leak continuously, not in a very high concentration and over a long period of time. So basically some systems like, as I mentioned, asparaginase, immobilized asparaginase has been inserted into the blood stream in the immobilized form, microcapsules, and the enzyme leaks slowly, and the system can remain in the immobilized system can remain in the blood stream over a few months. Of course, then again you have to give another shot to keep the enzyme activity available in the blood stream. So these methods can have an advantage that the reversible nature can also be used in some cases where you want to use them as a drug or a therapeutic agent, and with requirement of slow availability over a long period of time.
In the case of adsorption, we are losing the enzyme, but what the graph was showing was the deactivation of enzyme.
No, as far as our study of our reactor system is concerned, we consider, or we are not measuring the enzyme activity every time. What we are measuring is the conversion at the effluent, and we relate conversion is related to the enzyme activity. So that is why the graph is in the form of conversion. Now three most common types of adsorption methods are based on physical adsorption, which is again a most non-specific type of adsorption, where you use hydrogen bonding, electrostatic interactions, or van der Waals interactions, a variety of interactions where there is no specifications, and you use some a very broad range of carriers like alumina, cellite, bentonite, glass, etc., where which by at certain conditions of pH and temperature and salt, you can adsorb the enzyme onto the surface and they can be used. The second method is ionic binding, where you take a tailored matrix which has charge, a definite charge on its surface, and of course ion exchange reagents are the most commonly used matrices, DI cellulose, amberlite, etc., which are charged molecules, which are charged particles, and these charged particles based on the electrostatic interaction can bind the enzyme molecules corresponding if the net charge on the molecule at a pH where the net charge is counter, where the enzyme exists as a counter charge at a particular conditions. The third category is hydrophobic binding, where the predominantly we use hydrophobic interactions on the surface of the carrier and the hydrophobic interactions on the surface of the enzyme protein. The patches, the hydrophobic patches also, although you will recall that bulk of the hydrophobic patches and the hydrophobic residues are buried inside the residue of the enzyme, but still on the surface there are very small hydrophobic patches which can be used here for immobilizing onto the surface of a hydrophobic carrier, like carriers like polypropylene beads. In fact, there is a commercial product by the name Accurel, which is essentially a macroporous carrier consisting of polypropylene, butyl or hexyl saccharose, etc. There are a number of hydrophobic carriers used and which are available for binding of the enzyme. I must make here another pertinent point for information, that many of the carriers which are available today for adsorption of enzymes were essentially developed for chromatographic separations. For example, all the carriers like hydrophobic binding or ionic binding, as you will notice that they were originally developed for chromatographic separations, where the function is same. That means you are binding through ion exchange interactions, through ionic interactions, and desorbing it under conditions of desorption. So, therefore, the same thing applies here. In fact, the preparation of immobilized enzyme by adsorption is very much similar to chromatographic separations on ion exchange reagents. Although we are only interested in the first part of it, only adsorption part, desorption is not our interest. Whereas in the case of chromatography, we have both these parts to be of importance. Another important group of adsorption methods is, which I will also talk on, metal salt linkage. We will discuss that certain metal salts like titanium tetrachloride, ferric chloride, they form a kind of an inorganic bridge between the carrier on the surface of the carrier, and to which the enzyme molecules can couple. Again, the bridge that is formed, the linkage that is formed, what we have in the literature, what people have used is as a metal salt linkage. Of course, it is not a covalent linkage, it is a physical interaction, and thereby the enzyme is held, but has been very successful method from the practical point of view. We will discuss that in detail. Now, most of the adsorption methods, of course, can be characterized by the classical adsorption isotherms, and of course, depending on the nature of the carrier, nature of the enzyme that we are talking about, the isotherms may vary. Of course, three general types of isotherms that are known. One is linear, now where Q is the concentration of the enzyme protein onto the surface of the carrier, Y is the concentration, the corresponding concentration in the solution at equilibrium. If you take, let us say, a combination of an enzyme and carrier concentration, and at equilibrium measure the concentration in the solid phase and in the liquid, and you make an isotherm, then you may end up sometime in some cases a linear relationship where Q is equal to K into Y, which is simple relationship. Then the most
Sir, can you please explain how do we make this isotherm?
you take different ratios of carrier and the enzyme solution. To make the isotherms, what you do, you take different ratios of the carrier and the enzyme activity. That means E to carrier ratio, enzyme activity is varied, and at different combinations you allow it to equilibrium to be formed, and under equilibrium conditions you measure the concentration of the enzyme in the liquid phase and also in the solid phase, and so each point represents a particular ratio of enzyme to carrier ratio. And you can notice that you can find three different types of isotherms. Linear is most simple, Freundlich is most general in the sense that it does not fit into any physical hypothesis, but it is a general, you can make a curve fitting whatever kind of isotherm you find, you get you just raise to a factor n, and by analysis of your data you can calculate the value of k and n. If you make a log plot, you can get the value of k and n for any particular. The most established and analytically proven method is Langmuir isotherm. That is essentially, it is very similar to, now here Q is the concentration of the enzyme protein onto the solid matrix, Q naught essentially is the maximum capacity of the matrix. That means if you take a very high enzyme loading, very high enzyme concentration compared to carrier, allow the equilibrium to be established, that means and the concentration of the enzyme onto the immobilized preparation, which will represent the saturation kind of a behavior, is Q naught, and there you will notice that it is analogous to your Michaelis-Menten kinetics. The expression is analogous to, in fact these three expressions, the Langmuir isotherm, Michaelis-Menten kinetics, hyperbolic expression, and also the Monod's equation for cell growth, they are almost analogous expressions, and that indicates that there is some sort of interrelationship or some similarity in their basic physical interpretation. And of course, Langmuir isotherm is based on a theoretical development. One can develop on the basis of number of binding sites onto the enzyme molecule, onto the carrier molecule for enzyme. Here just like we consider the enzyme substrate binding, where enzyme acts as a carrier and substrate is the ligand. Here the carrier will be the matrix and the protein will be a ligand, and on those conditions you can develop it or you can analyze it by a double reciprocal plot. Like
Repeat, sir. The
the
analogy.
analogy is the three expressions: the Langmuir-Adsorption isotherm, the Michaelis-Menten kinetics, and Monod's kinetics for cell growth. They are analogous term. Now, what you have to develop an analogy and understand the relationship is that what are the corresponding terms. In the case of enzyme, we are talking of enzyme substrate complex formation. That means, enzyme is the matrix, surface is the ligand, surface gets bound to the, or in other words, if you talk in terms of adsorption, the surface gets absorbed, the substrate gets adsorbed onto the enzyme surface. On the other hand, here in the case of adsorption, the enzyme is itself a ligand and the matrix or the carrier is the surface on which the ligand adsorbs. In the third case, in the case of cell growth, the Monod's model of microbial cell growth, it is the substrate which is the ligand just like enzymes, but the matrix is the cell mass itself, and essentially it reflects essentially the transport of substrate into the cell. So, basically that is a transport, this is adsorption, that is transport, and enzyme catalysis, enzyme substrate binding. So, these three phenomena are intrinsically somewhere related, because they end up in a similar kind of a kinetic expression. And of course, as far as the analysis is concerned, all the three can also again be analyzed by a double reciprocal plot. That means, if you plot 1 upon q versus 1 upon y, you will get a linear plot, and you can get the value of q naught and k, and the adsorption isotherm, the adsorption process for a particular enzyme and for a particular carrier can be analyzed quantitatively. Now, many of the physical factors they influence the adsorption process. Some of them I have listed here. The first parameter is pH. Particularly, of course, pH will be a very major parameter which will affect the binding, will be in the case of ionic binding. Even for other forms of binding processes, pH plays a key role, and very often it has been noted that the enzymes, the binding or the binding by adsorption is maximum at its isoelectric point. And pH, but of course, a large variety of kind of relationships or with respect to pH for the quantity adsorbed have been found. There is no general ruling, but in general, or rather a common feature can be considered that the isoelectric point, the pH value will be most preferable for the adsorption process.
So, but at that particular pH, ionic bonding will not be feasible because the charge of the protein will be 0.
No, net charge is 0. Charge, it is not that the proteins are not charged at that pH. The net, the negative and positive charges are equal.
Practically immobile.
They are equal. They are not that I mean there is no charge on the matrix. Yes. The second parameter is salts. Many of the now salts have a very complex behavior. In fact, it has complex, almost opposite behavior. Also, you have seen, you must have studied also in the case of bioseparations, particularly salts. The concentration of salts are used also for increasing solubility as well as decreasing solubility. Salting in and salting out both are feasible, and of course, the phenomena or the physical interactions are just opposite. But in most cases, the salts concentration is required to be kept at a minimum. Otherwise, because salts are very good eluents also, even for those who have been familiar with the ion exchange chromatography, very often we use high ionic strength as a medium for elution of the adsorbed material. So, therefore, at the high salt concentration, adsorption is usually poor and minimum salt concentration is required to be kept. Protein concentration of course will be important, and we have seen from the adsorption isotherms itself a definite ratio of protein to carrier will play a particular equilibrium behavior, and protein concentration, higher the protein concentration you can reach nearer the saturation level at equilibrium. Temperature again is a very significant parameter, and which must be understood because normally if you look at adsorption of a small molecular weight material, small molecular weight ligands onto a surface, the general behavior is that increasing the temperature reduces the adsorption. That means the quantity of ligand adsorbed per unit weight of the carrier for low molecular weight ligands will be less as you increase the temperature, and obviously the reason attributed to this is because of the movement of the particles as the temperature increases. That means the movement of the particle increases, and the tendency is for desorbing rather than adsorption. But in the case of protein adsorption, when we are talking about enzyme, we are talking about protein, a macromolecule adsorption over a narrow range of temperature, it offers a reverse phenomena. That means adsorption increases with temperature. I mean, again mind the word, I am using over a narrow range of temperature increase. If you increase to a higher level, of course desorption also might start, but before desorption even inactivation might start. But we consider the adsorption at a narrow range of temperature, the increase in adsorption with temperature, the primary factors responsible are when the protein bind to a surface, there is some unfolding of the protein molecule, which is an endothermic process, and the increase of temperature resulting in enhanced adsorption supports the hypothesis that the binding of or adsorption of a protein molecule or a polymeric material to a surface is an endothermic process coupled with unfolding of the conformation. Mild, of course, when I say unfolding, I am not referring to totally deactivation, but minor modification on the conformation which extends its total volume or total surface area. The other factor which is important, which is probably attributing to this increase of adsorption with the increase in temperature, is the diffusional processes, because most of the time we are talking about the carrier being a porous material, and the ligands or the protein here had to diffuse into the surface, into the internal pore surface, and the diffusion process gets increased by increasing temperature. So both the unfolding of the protein molecule on the surface of the carrier and the diffusional processes involved in the adsorption in the internal pores ultimately leads to give you a phenomena which represents an increase in adsorption with increase in temperature over a narrow range. Then of course carrier properties will always depending on the properties like surface properties of the carrier particles, which were used as matrix, will also play a role on the adsorption behavior depending on the nature. Maybe sometime even the carriers are preconditioned, swollen to improve the properties, and the carrier will influence. And of course time of adsorption is another parameter which is significant and important, because again we are talking about the macromolecular adsorption. So the diffusion is involved, and the time required very often is controlled by diffusional limitations, and the rate of diffusion controls the time required for adsorption process, which in the case of a small ligand is not a constraint. Now practically for adsorption essentially we follow a number of methods, at least 4 major methods are used practically for adsorption in practice. The first and probably the most trivial method is the static process. That means essentially that you bring in an enzyme solution in contact with a carrier and leave it overnight or over a long period of time. Adsorption takes place without even agitation. Of course, it takes a very long time and that is the process very often very people use in laboratories, and whereas the yields are also much lower, particularly for porous carriers, because the diffusional limitations without agitation do not allow proper, and of course, the one of the most disadvantageous situation in this case is in the static process is that the loading of the enzyme is not uniform over the carrier. Even if you allow for a long period, but the loading is usually not uniform. On the surface it is large, and as the intensity decreases, if suppose this is a carrier particle, you have lot of enzyme molecules on the surface, but on the interior this is very rarely distributed, and so uniform loading is not uniform. The most commonly used method in the laboratories is dynamic batch process, in which you mix the two components, that the enzyme and the carrier, under known conditions or under standard conditions for adsorption, which favor adsorption, and agitate them, stir them mechanically under mild stirring, so that the carrier should not get degraded, carrier particle, and not also the enzyme molecules also should not be influenced, and it is allowed, and the equilibrium is allowed to be reached over a period of time, and it usually leads to a fast method and most common method used in the laboratories. The third method is the reactor loading process. Now, usually in the commercial establishment, when we use adsorption as a method of immobilization, we use reactor loading process. That means, the first of all, the reactor which is to be used for bioconversion or the enzymatic reaction is packed with the carrier itself, and then the enzyme solution is recirculated constantly through the carrier bed, and over a period of time the enzyme gets adsorbed onto the on the matrix, and it could be also not only packed bed, it could be also a stirred reactor in which the enzyme is added, and the solution is, the enzyme solution is allowed to be stirred along with the carrier, and after a period of time, when the supernatant enzyme activity has come to minimum value, you stop the process, and then of course, in all these methods which we are talking about, the final step is washing, because very often you will have that some of the enzyme will be adhering to the surface of the particles, which is not really immobilized in the proper sense, which is not adsorbed, but some adhering in the along with the liquid, and so a wash of the fresh wash of the buffer at a particular pH should be given, so that all adhering enzyme is washed out, and only that which is physically bound by adsorption is retained by the carrier. And obviously, the final washing also in the case of reactor loading process is done with the substrate solution itself, because essentially during the operation it has to be sort of meet the conditions, environmental conditions which are provided by the substrate solution, the feed. So, under those conditions it must remain adsorbed, and so the final washing in the case of a reactor loading method is provided by the feed substrate itself, so that whatever is desorption to take place under feed substrate conditions takes place, and the enzyme is in the stable form. The fourth method is electrodeposition process, in which the carrier is placed in proximity to one of the electrodes, and the current is applied between the two electrodes, and the enzyme particles which are charged, usually they get deposited on the carrier particles, and after at the end the carrier is removed, which gets coated by the enzyme particle. Only thing here we have to keep in mind a very important feature, that during the electrochemical process there will be certain ions which will be removed from the electrode or from the process, and therefore, if those ions are important for enzyme activity, then they must be provided in the electrolyte itself. A extra quantity of those should be provided in the electrolyte, otherwise you will not be having a functional enzyme preparation in the immobilized form. Now, the last method based on the adsorption process is by inorganic bridge formation, as I mentioned, or what we talked about was metal salt linkage. This was originally developed by a British group, of course Barker, Emery and Nobe, which one of the reference I have cited here in 71, and it involves a metal salt linkage. Now, the basic principle of the method is The method employs a transition metal salt like titanium tetrachloride, zirconium tetrachloride or ferric chloride for linking an enzyme to the carrier, and carriers are usually cellulose, nylon, glass beads, etc. The usual method is that an activated carrier is prepared by steeping it in a solution of transition metal salts for 5 to 10 minutes. I mind it that it is important because a longer contact of the matrix in the transition salt method, transition salt solution can result into degradation of the, because the pH of these solutions, like for example titanium tetrachloride, a solution will be very pH will be very low, almost 1 to 2, and if you put cellulose into it, it might get degraded totally. So the time of contact is very important, and it is not used steeped mostly more than 5 minutes, and if you take a dilute solution probably you can go further higher, but it is steeped and followed by filtering and drying of the complex at 45 degrees centigrade, and excess unreacted salt is washed with buffer, and the activated carrier is then stirred with the buffered enzyme solution followed by washing of the unwound bound enzyme. The method is very simple. This involves 2 steps: activation of the matrix by steeping it in a transition metal salt solution, and whereby the transition metal salts which form a kind of octahedral complex, and I think the chemistry of that can be considered like this. You know, in the form of titanium tetrachloride, they exist, titanium tetrachloride will exist in different forms, and the complexes will be either dominated by water molecules as the ligand in octahedral ligands, a complex form. The titanium tetrachloride solution, the salt will exist in different forms, complexed with certain ligands. For example, in the solution water molecules will be present as a ligand and will complex with water and chloride ions, and they exist, they are known to exist in the form of aqueous form, where titanium is 5 water molecules and 1 chloride form. It can also exist in the chloro complex, 5 chloride ions and 1 water molecule. It can also exist as total chloride ions in the case of a coordination complex. So normally when this solution is brought in contact with the matrix, typically let us say any carbohydrate matrix, cellulose has been a very commonly used matrix, then what happens that these ligands are replaced by the hydroxyl groups present on the carbohydrate molecule. The ligand, particularly the water molecules which are present here, are replaced by the hydroxyl groups present on the carbohydrate molecule, and you make a network of a titanium treated cellulose which is complexed along with the length of the chain on the carbohydrate is formed. Now when this activated, what we consider this is an activated complex, an activated matrix. Now when this activated matrix is further brought in contact with the protein or enzyme, again some of the water molecules are replaced by the functional groups on the enzyme, and it forms wherever you see water molecules, for example these ones, they may be replaced by enzyme molecules. Wherever hydroxyl groups are present, they can be replaced part of them, and essentially what ends up is essentially a matrix which has a coordination in link of titanium tetrachloride salt along with the enzyme molecule. And essentially one of the major advantage here in the case of this method is one of the major advantages that you always end up having a distance between the carrier surface and the enzyme molecule, because enzyme molecule and the carrier surface are separated by these linkages, the metal salt linkages, and that provides you a very big advantage of steric hindrance, removing the steric hindrance. Many of the enzymes, when they are coupled to a solid matrix, may not be able to interact with the substrate because of steric hindrance, but in this case because there is a distance between the matrix surface and the enzyme, so steric hindrance is minimized. And the second major advantage which has been noted in these cases, that if you use the regenerated carrier after the enzyme has been, let us say, leached out, there is a regenerated carrier and you again immobilize the enzyme, it gives you a much increased activity, and that is a major advantage. That means basically, and the major reason has been that the distance from the surface has increased, and so steric hindrances are further decreased, and therefore, particularly with those enzymes which are known to have steric hindrances during immobilization, that means with which one, the ones which use much larger polymers as the substrate, for those systems, the method provides you a very significant important method. So, these are the various methods what we have discussed today, the various methods that involve the coupling of enzyme by adsorption to a matrix and their characteristic features, and of course, as I mentioned that the immobilization methods must be checked, must be sort of evaluated on the basis of their yield, operational stability and carrier regenerability. So, we stop here.